All right, so now that you guys have mastered the hard part, going from this combination of substrates to the product that's going to be formed, or working backwards from this product's being formed, what are my substrates that I'm starting out with, we're going to complicate things a little bit. Okay, specifically, like I had talked about before, these reactions occur between a diene and a dienophile. We're going to talk about what makes a good dienophile. Okay, it needs to have an electron withdrawing group. Otherwise, it requires too high temperatures, which leads to a really poor yield. So we can have this very simple reaction between 1,3-butadiene, right? 1,3-butadiene and ethene. The only problem is that it's going to require high temperatures, which actually favors the reverse reaction. So the max yield that we're going to get is something like 20%. Okay, which isn't nothing, but it's not great. We can increase the success of this reaction if we add an electron withdrawing group to the dienophile. So what would be an electron withdrawing group? Anything with a carbonyl group, well, I guess that's not really, with a carbonyl group or a cyano group, a cyanide, right? And so that could either be, this would be a ketone or an ester or a carboxylic acid, or this, again, it's a cyano group. Any of those would be electron withdrawing groups. And by adding that to your dienophile, you can get to 100% product formation, right? 100% yield. Really helps drive this reaction forward. Okay, electron withdrawing, which means that it's going to pull electrons towards it, right? So that's going to be one of these reasons we need, if we're going to do our mechanism, we need this guy to jump over here, this to come down here, this to come over there. So you're kind of enticing these electrons outside of their existing ring with that electron withdrawing group. Okay, these are going to be the 4 examples of the electron withdrawing groups that we're going to see. So number 1, add an electron withdrawing group to increase yield. Okay, so now let's talk about regioselectivity, or the constitutional isomers that are formed. If either your diene is symmetric or your dienophile is symmetric, there's only one possible product that can be formed. So both of these examples you guys should be able to readily do based on what we saw last lecture and did in the activity, the associated activity. Now we're going to complicate things a little bit, because what happens if both your diene and your dienophile are asymmetric? Then what do you get? So it turns out that there's 2 possible products that you could get. And we have 1 major product and 1 minor product, right? So there's something deeper at work here that's leading to one of these conformations to be favored, not conformations, one of these constitutional isomers to be favored over the other, okay? And what is that? This is going to be especially true when the diene is substituted with an electron donating group. So whether that would be, so let me just give some examples of electron donating dienes. That would be something like an ether, an alcohol, or an amine of sorts, whether it's primary, secondary, tertiary. All of those groups have a pair of electrons to donate, and they're really going to lead to the regiospecificity of these reactions. Right, so these are electron donating on your diene and electron withdrawing on your dienophile. That's going to lead to this very specific reaction where you get like some 90-10 distribution of major minor products, something that really favors one of these 2 constitutional isomers. So let's look at why that is. Okay, it has to do with the different resonance structures that are available to these molecules, right? So if I'm going to draw the other resonance contributor for my diene here, this pair of electrons can come down, and this pair of electrons jump up onto that carbon. And that's going to lead to this resonance contributor here, where notice that there's this negative charge on that top carbon. Now, that's not the most stable resonance contributor by any means, but as I've said before, any resonance structure can play an important role in the chemistry of a molecule, even if it's not the dominant one. And then when we go to our electron withdrawing group, I have this similar sort of thing where this pair of electrons can jump up onto this oxygen, right? And then this pair of electrons from that pi bond can go, I don't like it pointing there, I want it pointing at the actual carbon, can jump up there, and we get this resonance contributor here, where this carbon has a partial positive charge, right? So in my diene, it has this resonance structure available where one carbon has sort of an excess amount of electrons, an excess amount of negative charge. And likewise, my dienophile has this resonance structure available to it where it has this excess amount of positive charge or a deficiency of electrons. So the regiospecificity of this reaction is a result of these two resonance structures, the one for my diene and the one for my dienophile. Basically, these carbons want to be lined up next to each other, because this carbon over here for my diene has this excess amount of electrons, and this carbon over here is relatively electron deficient, right? It's got a partial positive charge. So this is going to help drive this first reaction, or this first motion of electrons, where this pair of electrons jumps over here, which then kicks off this sequence of concerted events where now this pair comes down here and this one jumps up here. So because these two carbons, the partially negative one on the diene and the partial positive one on the dienophile, want to be right next to each other in kissing distance, and that will help promote this electron, that's why we get that as our major product. Okay, where the electron donating substituent, right, that would be this guy here, is on the opposite side of the electron withdrawing substituent. So this one was electron donating, and this one was electron withdrawing. And they are on opposite sides when you consider the fact that these were our two newly formed bonds.
All right, so this was a good question about the stereochemistry of these Diels-Alder reactions. So what we talked about in the lecture slide is that when you have this electron donating group over here and an electron withdrawing group over here, that the different resonance structures are going to be what leads to the actual stereochemistry of your major product, right? Because these are asymmetric substrates. So depending on which way they're turned, I'm going to get a different product. So because these electron donating groups have this pair of electrons to donate, that will lead to a partial negative charge on this carbon. Likewise, over here, this particular functional group is electron withdrawing, will accept a pair of electrons, and that will leave this carbon with a partial positive charge, okay? So those partial positive, partial negative want to be aligned. So to get this correct stereochemistry for this product, for this reaction, I would have to turn this other substrate, my dienophile, around, okay? Now this is going to be the sequence of events that gives me my correct stereochemistry. There should be a double bond there. Cool. All right, but if instead of starting out with our substrate on the 1, 2, 3, 4 on the carbon 2, I didn't think to do this other example where the substrate was actually on carbon 1, And here it's the same principle, but you get a little bit different of a product. So again, I have this electron donating group. That's what these guys are. Notice how they're different, obviously, but they have that pair of electrons to donate. Here, this will sort of kick off a resonance structure. Well, again, where again that functional group is donating electrons, so it's pushing it down onto that carbon. But that'll actually kick all of these around such that it's this now carbon 4 that has a partial negative charge. We want to do the other one for the, it's this carbon that has the partial positive charge. So then I won't have to flip this around, although I will redraw it just because then there's a ton of arrows going on. But now the sequence of events is going to be in this direction here. So in this case, you get the 1,4 product as the major. And in this case, you get the 1,2 product as the major, right? And by that, I mean, how far apart are these functional groups? Cool.
Okay, last bit of, this is actually stereochemistry, but last bit of complication to add to this Diels-Alder picture here is having to do with the formation of bicyclic compounds. Remember last lecture we were saying that if we start out with a cyclic diene, so in the case of pentadiene, for example, hexadiene even, we're going to get a bicyclic compound that's formed. And again, if I'm going to sort of just color code which carbons, and actually let's make this guy special. He can be purple. Started out on my pentene. Well, maybe that's a poor color choice. Let's make it green. All right, so that I can follow these in the next step. I'm going to draw my reaction mechanism just like I would before, making sure to start my base of the arrow at a pi bond and the tip of the arrow at an sp2 hybridized carbon. Boom, boom. Now, if I'm going to go and trace those same carbons out in my bicyclic product, those are the green ones, and then my purple one at the tip there, that's the one that's now pointing straight up. Okay, my newly formed bonds are these ones here. All right, but in those bicyclic compounds, if I start, and this is actually specific, we'll do an example at the end. If you start out with a cis dienophile, is you could have two different stereoisomers, what we call the endo isomer or the exo isomer. How do you decide what's endo and exo? We are going to look at this bicyclic compound and look at these two bridges, what we call bridges. The one is composed of that single carbon that was at the tip of that pentadiene, and the other one are these two carbons down here. The bigger bridge, which is the one with two carbons, is what we're going to name things relative to. If it's syn or on the same side as the big bridge, it's endo. And if it's on the opposite side of the big bridge, it's exo. Okay. One of these two is actually more favorable than the other one. All right. It's actually a little surprising, at least to me, which one is more favorable. It turns out that the endo product, or where your substituents are on the same side as the big bridge, is more favorable than the exo products. Like notice how this one's exo because it's same side as little
bridge, which is this one here, versus exo, same side as big bridge, which is here. Okay. The endo product is actually more favorable than the exo product, which is a little surprising because we would think that we would want these big bulky substituents to not be next to the big bridge. You'd think you'd want them next to the little bridge. On the one hand, actually, let's look at this one too. On the one hand, it's true, the exo product is lower in energy than the endo product. So it is, in terms of sterics, more favorable, that exo product. However, that delta G double dagger, that was like a hashtag, delta G double dagger of the endo product is much smaller. So the endo product is much faster to form, which is why it's more favorable. Why is that? It has to do with the fact that while these two products form based on whether or not, based on the orientation of the dienophile, so just notice if it's pointed such that those electron withdrawing groups are sitting underneath that cyclopentadiene, that's what leads to the endo. Versus away, that's what leads to the exo. And it just turns out that having those electron withdrawing substituents sitting underneath that ring structure is really favorable. And so that's what leads to the fast formation of the endo structure. The bottom line is the endo product is the more favorable one. Okay. This is not the case when you have a transdienophile. Then you don't have to worry about that. You're going to get a mixture of both. You're going to have one position that's endo and one position that's exo, and then you're going to have its enantiomer where they're reversed. I tried to draw it. It was so ugly. So yeah, I'm just going to write plus enantiomer for now. But yeah, if your dienophile is trans, you don't really have to worry about it. But if it's cis, it's always going to favor that exo product.